All right, so we're here going deep, um, and we're going to talk about Windows. And we're down in kernel mode, and we're talking with Molly Brown, who is a engineer who owns a cache manager. Welcome. Thanks for talking to us.
Thanks for having me.
So, can you tell us a little bit about what you do?
I am a software design engineer in the core file services team of Windows. That is the team responsible for all the local and remote file systems and the logical layer of storage devices. So not the drivers to run the actual devices, but things like the volume manager and the mount manager to manage mounting and dismounting of volumes, and all of the software, RAID, and mirroring support, and those types of things in the operating system. I specifically work on the cache manager, which is the interface between the file systems and the memory manager, and it provides it does logical file caching for all of the local and remote file systems that ship with Windows.
And so that's basically disk blocks, managing when to...
So as a logical file cache, as opposed to a disk block cache, we cache things at the file layer. So we are sitting somewhat kind of to the side of the file system. The cache manager understands files as streams of bytes, not as the blocks as they store on disk. Okay. So that gives you a few benefits, namely that we can do more intelligent read ahead, because we can guess where we can pre-populate the cache based on file offsets, because people very typically read through files sequentially.
Okay.
Whereas a disk block cache, while it may be logically block data offsets will be logically contiguous, they will not necessarily be physically contiguous on the media, and so that is abstracted from us. So we get benefits. There.
So now, is this different than how it was in NT4?
No, the cache manager is always.
It's always been the same.
This way. Yeah.
Now, how do you figure out when to pick something from the cache and when to call the file system and say, I need this, I've been asked for this, but I don't have it in the cache, or
So the cache manager is, in some sense, just more like a library that file systems use. So the file systems initiate when setting up caching on a given file based on the types of requests that have come down from the user. And by default, when you use read file, write file at the Win32 API level, those will result in cache, or buffered is the word they use in Win32 terminology, buffered IOs. And so we will, at that point, the file system goes through the cache manager APIs to read the data or write the data, and that brings the data into the cache and initiates read ahead that we're going to do, and all the behaviors that the cache is going to do for you.
And so there's no sense of sort of trying to anticipate what something's going to be, whether or not. Not other than we do read ahead based on the read patterns that we're getting, okay. But those are we have to essentially see a few reads before we'll start doing the read ahead. There's other functionality in the operating system to provide just general prefetching of data in cases like boot time and application load, where there's something that's dynamically tracing I/O patterns and trying to prefetch before there's any hint that something's going on. And that's a good point that you raised, because NT allows for multiple file systems. So someone doesn't have to also write a cache manager. They can just hook into a global one that you're nice enough to provide. And just kind of give you some hints as to tell you what they're going to need, etc. And you handle all of the I don't know, you don't call it buffering down at the kernel.
all the buffering, caching. Yeah, it's the same. It's the same.
Okay.
Same thing. I usually translate.
Yeah. So you do a lot of work with the virtual memory manager.
Yes.
Correct. So can you kind of paint us the picture of what your world is like with
with the I guess the easiest way for people to understand what the system cache does, it is actually built on the same infrastructure, file system infrastructure that most developers are used to already using, memory mapped files.
Okay.
And actually this would be a good time to drop.
All right.
The
Fantastic.
system cache basically it has a portion of the kernel virtual address space that has been reserved by the memory manager for the system cache. And these are they're addresses that are only visible in the kernel virtual address space. And the cache manager breaks that virtual address space up into 256 kilobyte chunks, and then the cache manager memory maps ranges of the files into these different ranges of virtual address space as the files are accessed. So if you imagine we have all of these blocks, which we call VACBs, virtual address control blocks, that track the file, and they track the file mappings to, so the file offset mapping to the virtual address that will actually be used to address that range. So you end up having, so say you have file 1 and you only are touching this portion of the file. It's represented essentially by, we map this to some section of our VA space. You can have another file that is also being accessed through the cache, and you're touching a different range of that, and that could be mapped to a different block of the system cache address space, and they're always in 256K chunks. And so for a given file, it'll be spread out amongst the system cache virtual address space, but and it's always accessed within those 256K
Now,
line
what
chunks.
is the reason for the 256K requirement per block?
We basically are making a trade-off of how much metadata we need to store, or how much the internal control structures for the system cache. Plus, there's an expense involved in talking to the memory manager and saying this range of the file should map to this virtual address space, and that is relatively expensive in terms of locking and synchronization in the operating system. So when the original designers of NT were working on this, they decided that 256K was the right trade-off of space we need to store our control information about the file system mappings, and also a good unit of granularity for performance reasons.
Sure. And brings up a good point. Since you're always working in the kernel, you are very attuned to concurrency.
Yes.
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 So that's something we've already talked about a lot. That's the new big thing now, especially for those of us way up there. So.
Yes, that is pretty much that basically almost all the problems I deal with have some issue of concurrency involved in them. I deal with a whole lot of performance issues, trying to track down why things seem slower than they were before, or how can we make them faster in certain scenarios. And it almost all comes down to scalability and our locking hierarchies to provide better parallelism.
And clearly you're writing in C.
Yes.
Probably strict C.
Yes.
Now, I don't think there could ever be anytime soon a managed cache manager, but it's something, very hard to pull off. I always talk about that because the idea of managing this down there is interesting. I know some people would never want that to happen, but it's interesting. Cool. So, what else? What other components do you work with on a regular basis down there? Of course, the file system.
The file systems. Yeah. So the file systems the main method of communication between the cache manager and the file systems is through a file object, which is the structure that all the drivers see. And so within a given file object from the file system will store on behalf of the cache manager a shared cache map, which and a private cache map. And so the shared cache map provides basically you have all these file objects. And you can have multiple file objects that are representing the same physical file on disk. And so say this is file object 1 for that file, and this is file object 2. They'll have the same shared cache map. They both point to this shared cache map. And so that is basically the cache manager's metadata and control structures for this stream while it's in memory. So if 2 users are using the same file, we keep the data coherent and consistent across those 2 views. This also allows us to only cache the data once, because there's no need to cache the data multiple times if it's just being used by multiple applications, multiple users at the same time. But each file object also needs to have a little bit of private information for that particular use, and that we put in what's called a private cache map, and that tracks our information that controls our read ahead, and that's the only thing that is in the private cache map. But we track, we use the access patterns of each file object to determine how we should read ahead. So if these 2 users or 2 applications are reading at different sections of the file, we will read ahead for each of them individually.
Very interesting.
As I said, the memory manager pre-allocates a range of virtual address space for us. And so therefore we have a limited amount of virtual address space to use for the system cache. And that space, since especially on 32-bit machines, the kernel virtual address space is only 2 gigabytes, and the maximum configuration for the system cache, you can allocate, I think it's about 550 megabytes worth of that 2 gigabytes worth of space. These days, files are much larger than that, so so you run into a problem there. And the way this is handled is the system cache contains the data in the system cache not only sits in the virtual address space that's actually reserved for the system cache, but when it's not actually mapped into the virtual address space, it's sitting on the memory manager standby list. So as long as that physical memory isn't used or repurposed for anything else, the data's sitting there. So the next time that range of the file is accessed, we'll just find a free space in the virtual address space and map it back in, but we don't have to read it back in from disk. And so that provides a great performance benefit. So you do see better, you can cache more when you have more RAM in your machine because of that.
We'll edit this out.
I actually probably won't. But that brings up a really fantastic point. I was just yesterday at the Route 64 training.
Yes.
So clearly, 64-bit Windows involved everyone in the kernel having to rewrite some code, correct? So you now don't have that limitation that you just mentioned.
Right. For the cache manager, there wasn't a whole lot of architectural changes that were needed to support 64-bit. There are some just at a low level, you need your data structures aligned slightly differently for 64-bit machines, and the various architectures have different requirements, so there's changes at that level. But the architecture scaled to that. But now that does allow us to look at changing this design, because a lot of the design options that were made for the system cache for when it began to design on a 32-bit operating system, where a few megs of RAM was a lot, aren't true any longer, and so there are different trade-offs we would like to make, and that's actually a lot of the work that we're doing in Longhorn, is how can we better make use of the hardware resources that are typical today, because a lot of the assumptions that were made 15 years ago don't hold true any longer. But it does still. But these algorithms do still work. They cover the majority of the cases, and it scales well. We do have. It works on 64-bit operating systems. The benefit is now this VA space is much larger than it was before. So some of the cases where we get into basically a lot of contention on the view space, trying to unmap one view to get another one in and kind of keep doing that swap to meet the user's demands. We don't have to do that anymore. We have plenty of resources.
Which will bubble up for the user as more performance.
Exactly.
And that's, and because a lot of people do wonder, well, 64-bit is interesting, but besides SQL and Oracle and these other data-intensive applications, how's it really going to benefit me? Anyway, I mean, that's a really kind of explicitly deep point as to exactly why. Interesting, great. So, excellent. So, well, that's great. We covered 64-bit. That's important. What other kind of new? Are there any new innovations you're working on for your specific role?
Mainly for Longhorn, we're focusing on better tuning for performance issues, and then so that it's a lot more getting better performance for simple things like copy file, and there's more. The system's getting smarter. We're putting in more infrastructure to be able to kind of tune the system based on the demands of what's going on the machine right now, and so making our algorithms more adaptive and how we behave based on what is happening in the system versus registry key settings, or somebody has to understand and tune the OS for their workload, and they have to understand what that means if that for the system cache size versus paged pool or non-paged pool usage, and all of these things, which truthfully even elude some of us who know it in great depth, exactly what the right settings are until you actually measure how the application's working. And so we're working to remove a lot of that layer of kind of low-level tuning and let the operating system be just much more adaptive.
Exactly. I love hearing that. So, more adaptive operating system. So it's actually going to learn a little bit. In other words, when you said, like when you just described, when we watch the patterns of an application, it's actually going to be the OS watching these patterns and making an assessment and then fixing and then sending instructions for how to handle this next time the file is invoked, etc.
Exactly.
So that's beautiful.